Good morning, good afternoon, good night. It's 2 p.m., 2:01, so we might wait a few more minutes and then we can start. We have our speakers, Mr. Georgit Roy and Professor Wenzing Kuo. And we also have the VP of the Technical Committee Board, Cheng Hong Dixon Lin, and we also have officers of the 15 technical committees. So in a few minutes we can start. Okay, welcome to this webinar of the Technical Talks of CTSoc series. This is the 23rd event of this series, and I'm Fabrizio Lamberti. I'm the chair of the Technical Committees Board and the VP of Technical Activities of CTSoc. And today I will give you a brief introduction of the technical activities area and present you this series of events. So basically, the technical activities area is one of the areas that characterize any society of IEEE, including the IEEE Consumer Technology Society. This area is made up of the technical committees and the Future Directions Committee. Let's start with the technical committees. These committees have been established at the end of 2020, in the beginning of 2021. We do have currently 15 TCs. As you can see, they are covering various areas of consumer technologies. And today we have representatives from two of these committees, the CCN, which is Consumer Communication Networks and Connectivity, and the IoT, Internet of Things, Internet of Everywhere, and Edge Computing. These committees are part, as I said, of the technical activities area, in which we do also have the Future Directions Committee, which is in charge of identifying new areas of interest for the Consumer Technology Society. The technical activities and its committee as a board. And within this board, we have also Vice Chair, Professor Cheng Hoon Dixon Lin. We have CTSoc President represented, the VP Conferences, VP Publication, VP Industry and Standards Activities, and recently also VP Educations. Plus, we have the officers of these 15 technical committees. So first of all, let me show you the officers. So each TC has its own chair, its vice chair, and secretary, and they have their own page where they have the mission and objectives. We have the list of members who are part of this family. And basically, if you are not yet a member of the technical committees, you can join or you can suggest your colleagues and other potential interested researchers and industry representative to fill in this form. So basically, currently we have something like 1,600 members of these TCs, which are just a part of the membership of IEEE Consumer Technology Society, and many of these TC members are not even members of CTSoc and IEEE, because basically we do have overlapping set of potentially interested practitioner, researchers, academicians that wants to work and are interested in these areas. What is the roles of the technical committees and the technical activities? So basically, it's to support all the other areas of CTSoc. I mentioned it, the VPs of conferences, of publications, of standards, education, and history. So the idea is that these VPs and the technical committees themselves are the engine of these other areas of CTSoc. So what are the technical committees doing? Well, people involved in the technical committees typically is selected to serve in conferences organized by CTSoc. They are selected to help with the associate editor positions in our publications. They organize special sections in journals or workshops and special sessions in conferences. They are involved in activities connecting CTSoc with other initiatives in IEEE, like the IEEE Digital Reality, the IEEE Digital Privacy, or in collaborations with other society like SPS, AES. They launched special interest groups like that on the metaverse. They are contacted and invited to become distinguished lecturers to give talks like the ones you will be listening to today. They participated in two projects, like funded projects, like we had student internship projects, and we are thinking about doing something else. We worked on joint papers, newsletters. We are working on implementation on standards. So if you're interested, please check the main CTSoc website. Go on the, I will show the QR code in a while. Go under the membership application form for the technical committees and apply. Um, just let me advertise some of the events you might be willing to contribute to. So these are conferences with open calls. Let me remind the flagship ICC Taiwan conference, the ICC conference in Berlin, the GEM Gaming Entertainment and Media Conference that this year will be co-located with ICC Berlin, and the Global Conference on Consumer Electronics in Japan. So these are some of the conferences you might be interested in being involved in too, as author, as a reviewer, as a member of the committee. And same advertising for our publications, transactions on consumer electronics, and IEEE Consumer Electronic Magazine. You can go on the website of these publications and see what they offer. We are gonna renewing now the list of associate editor and senior editor of Consumer Electronic Magazine. So the new terms will be opened in a couple of years, let me say. But there are, for instance, open call for special issues, and in case you want to submit to the main tracks to these special issues, or you want to propose anything new, please let us know. Coming to the technical talks, and this is my last presentation slide. So the technical talks is an initiative that stemmed from previous initiatives in individual technical committees, and we realized that it would be nice to have webinars, 1 hour long webinars with speakers from two different TCs capable to attract an heterogeneous audience. So we started, as you see, a couple of years ago. We have now webinars every month. The next webinar will be at the end of June, so stay tuned for the detail. Today, we do have great speakers from two different TC, as I said, the IoT TC and the CCN TC. But I will leave, of course, my colleagues to introduce them. Let me thank anyway Mr. Jojit Roy from Austin, Texas, and Professor Wenzing Huo from Yuanzi University, Taiwan, for their great speeches. So let me stop here and let me leave the floor to Dixon or the TC officer who wants to introduce their speakers. So Chang, and maybe we can keep the order. So Jojit first, and then Wen Xing. Who is going to introduce Mr. Roy? Dixon, do
Okay,
you
I
want to?
will.
Yeah, thank you.
Okay, thank you. It's my honor and a pleasure to introduce the speaker from IOTTC. And Mr. Joy Rowe is a senior technology and program management leader with over 21 years of experience in enterprise digital transformation, cloud modernization, and applied AI, focused on agentic AI architectures, autonomous decision systems, cybersecurity automation, and enterprise scale AI governance. He currently serves in a principal level leadership role, leading large-scale modernization programs that integrated machine learning, intelligent automation, and agile delivery frameworks across global enterprise. His technical and research interests include applied AI and machine learning, natural language processing, multi-model systems, computer vision, agentic AI, edge AI, cybersecurity automation, and intelligent workflow orchestration. Uh, his work focused on translating emerging AI capabilities into scalable enterprise solutions that improve decision-making, operational efficiency, and organizational resilience. Mr. Roy is a senior member of IEEE and a fellow of the British Computer Society and a fellow of the Association for Project Management. Let us welcome his speech. Thank you.
Thank you, Professor Dixon. So let me share my screen.
Thank you,
And let
Dixon.
me know if you are able to see.
It's coming.
Yeah, is it visible?
Now, yes.
Yes, yes.
Okay, now it is perfect. So, uh, great. Good morning, evening, afternoon, and night. I know like a lot of people join from different time zones. So thanks again, to Professor Dixon to introduce me. I'm Georgit, obviously an independent researcher, right? So today I'll be sharing actually research work. It's a framework that called Safe Driver IQ. This is actually a real-time driver safety scoring system. So built on connected vehicle IoTs. So I'll go through more details. Let's start. Okay, a quick table of contents. I'll start with the motivation, the safety problem that drivers has, in current time, right? Then I'll show where existing approaches that to make those problems resolved has fall short and why we need something like, different. Then I'll introduce the Safe Driver IQ research framework that my team and I built to solve exactly this problem. Further, I'll walk through our data and methodology, share the key results and findings, followed by the conclusion and the real world impacts along with future detections. So moving forward, okay. So let's start with the problem statement. So do you guys know that more than 1 million people die on road every single years worldwide? Right? More than 1 million. Precisely as per the data of World Health Health Organization 2023, it is 1.19 million, right? I have some US number here, right? But all the other countries also have these numbers really, high. So in the US, pedestrian fatalities have increased 50% over the last decade, right? Uh, More than 7,000 pedestrians died in US in the year of 2024 itself, right? So this is actually a huge number, and these numbers are not going down. So basically, they're going up year after year. So now here, the real problem is, despite all the technologies, the latest technologies that we have today, more safety incidents are happening, right? So most safety systems still give you a binary answer, correct? So crash luckily or crash unluckily, something like yes or no, right? So before a crash happens, even when they analyze the crash reasons, mostly the outcome would be there is a possibility of crashes, but it doesn't have the details that what are the multiple factors that cause the crashes. Okay, so that's it. No degree of risk, no real-time guidance, no way for a driver to know how dangerous their current conditions actually are. So, like, think about this way: you have a GPS, right? You use the GPS to drive from one place to another. You not want your GPS to just say you might not reach to your destination, right? So you want to say it like take a different routes or a detour, right? If there's a problem ahead, and then give you a new directions, right? So road safety actually needs same kind of shifts rather than just a yes, no, or accident probability of the accident will happen or not, right? So when drivers or fleet operators or planners actually need, so what they need is actually a continuous explainable scoring system that tell them how safe conditions are right now, not after the crash has already happened. And that gap is exactly where our research addresses. So moving to next slide. Before going further, let's discuss what the existing approaches are in current industry and why they fall short. So before walking through the table, this table that you see on the screen, let me define one term, VRU. So which means vulnerable road users. So they are mainly pedestrians, cyclists, sometimes motorcyclists, because they are more exposed to crashes than people inside vehicles or cars, right? So there are five main approaches in this space as of today, right? So including ours. So let me go through one each of this real quick. So crash prediction ML model. So this is actually ML model, mostly accurate, but they only output in binary yes or no format. No degree of risk, no real-time feedbacks. As you see on the screen, real-time, continuous, VRU focused. We just talked about what VRU is, and interpretable, right? So it just tell you the possibility. Next thing is telemetry scoring system. So that use vehicle data like speed, braking accelerations, GPS, and hard turns to score how safety someone is driving, right? And another is Bayesian models. This is actually a probabilistic model that estimate risk in real time by updating crash probability as new roads, traffic, or behavior information comes in, right? So if you see telemetry scoring and Bayesian real time or Bayesian models, so they both do give real time continuous scoring. Both are yes and yes, right? But they are not actually very focused, and neither they can explain why they feel there will be a crash. So there will be less interpretability, less or no interpretability or explainability for both telemetry scoring and Bayesian real time. Next, the fourth is user-based insurances or UBI. This is nothing but an insurance programs like or app, right? That track driving, that install in your mobile and track driving behavior through phone, vehicle, and adjust premium or discounts based on how safe, how often, and where the person drives. So look at this road. row, not the last, sorry, UBI system. So it is actually the worst of all. So it is not real time, not continuous, and no VRU error. And look at the last row, the safe driver IQ, the proposed model. So it has all the all the four capabilities together. It's real time, continuous, VRU focused, and interpretable through sharp values. So that gap is what we set out to close, and it is what makes this framework actually genuinely new. Moving to the next slide. Now let's discuss the architecture, a quick one, right? So basically this is actually a flow diagram, not the architecture. The next page has the architecture. So at the core, this is a framework that takes binary crashes classifier and transform it into a continuous 0 to 100 safety score, right? Again, it will, the output of that, this entire framework or model is a continuous 0 to 100 safety score that a person can actually use. So if you see this pipeline or flow diagram, it has 5 stages, the stage 1 and stage 2, right? So we combine 2 data sets. The first one is NHTSA, so National Highway Traffic Safety Administrations. So that data set, we used 417K records over 8 years of crash data. So the red you see NHTSA, it contains crash data, and we use 8 years of crash data. And then we use another data set, WAMO, Open Motion Driving data sets. And this data sets use a lot of real world scenarios. We use 500 real world driving scenarios and combine both the data sets and then fed into the model classifier, random forest model classifier, right? So that is the stage 3, that is the ML model, right? So definitely it's a tree-based model. So it has the capability to take decisions, right? And explain, we'll come to that actually, explain why the decision has been taken. That's why this model has been chosen. Stage 4 is the key trick here. So instead of using the classifier to predict crashes, we invert it. So basically what happened, if we call, it's called invert scoring. So for example, if crash risk is 30% on a given incidence at a given moment, then the safety score is 70%, right? So we invert it. We multiply the probability of a safety outcome by 100 and get a continuous score from 0 to 100, right? So as you see, the safe score, we multiply to 100, and that probability comes into a continuous score from 0 to 100. We have a calibration to on top of this score, and we'll discuss that calibration later, right? So we need to go a little deeper to understand that calibration. Stage 5 is sharp explainability. Every score comes with a reason, right? So why is your score, you scored this? If you consider the safety is low or risk is too high. For example, it is lightning, weather, bad weather, like say, speeding, the person driver is speeding, or vulnerable road users or VRU are present, right, at that moment. So the bottom, you see, row shows 3 deployment paths. Actually, here in 3 areas, we can deploy this whole framework. First is the ADS. You might be familiar with ADS, Advanced Driver Assistance System. So most of the latest vehicle have this. For an example, automatic braking, lane change warning, or in-vehicle safety alerts. All this comes under this ADS system, right? So you can deploy this framework there also on your dashboard. Say it shows your score, safety score. Currently, no vehicle has that, right? I'm talking about practical implementation kind of situation, right? So no modern vehicle has that kind of display, that how safe you are, what percentage it is showing, or something more meaningful, that kind of like bad weather, right? Or some kind of message in very short. Second is the fleet managers. So these are companies or terms that manage many vehicles and drivers and can score entire driver population continuously. It is not just flag incidents after they happen, right? So, and the third is the insurance telemetries, right? So these are apps, as we just discussed, of insurance companies that use a scoring system to adjust premiums, discounts, and risk, right? So finally, they can deploy this framework in their app, and they can move beyond one size fit all premiums to pricing that reflects actual driving conditions, not just how far someone drives and what road conditions and how frequently, right? So this is something, the three deployment areas that can be targeted. And this is what the flow of this new framework is. A quick architecture. So there are two phases, obviously, training phase and the inference phase. The top half is the training phase. And as I told just, in previous slide, we use two data sources fit into, one filter, right? VRU filter. And we sample the data set and we used more than 46K records to train the model. Definitely, we have feature engineerings, and we have 64 features grouped into 7 groups. So these 64 features are nothing but the different cause of accidents, right? So there could be 64 different types of accidents, right? We'll come to that. Definitely, we fit the data into our, random forest, and then sharp value is applied on top of the interpretability. For the interpretability, I mean, right? And the bottom half is the inference phase, which runs in real time, all right? So live driving context from sensors, GPS, camera, weather API, and many other sources comes continuously feeding into the, in your vehicle, right? So, and in this training model, the vehicle contain the training model, that I mean, right? And then which then gets inverted into a probability scoring, pass through a calibration layer, and is returned as an output from 0 to 100, right, as a safety score. So, and all these things, during the real time, all these 4 steps happen in less than under 1 millisecond, because it has to be very real time and it will be continuous evolving, right? Okay, so let's move on. Next, we'll discuss the data strategy in little more details. And that is because it is one of the novel part of this whole system. So two data set, right? Crash records alone are not enough. Correct. So in NHTSA, it has crash records, but it is not enough. So they tell you one part of the story, what went wrong, but not what a normal driving environment looks like. So that's why we need to introduce that Waymo database, right? So the left side is the NHTSA database. It has, we used 400, more than 417K records. Out of those 417K records, more than 23K records VRU specific, vulnerable road user specific crashes. All this data are actually US road types, based on US road type, and cover all types of, roads in US. And definitely the whole this data actually brings breadth, statistically representative view of crashes across all US road types. And whereas the Waymo data, we use 500 real world driving scenarios with high resolution trajectory data at 10 hertz. It captures vehicle, pedestrians, cyclists, sometimes motorcyclists, and importantly, near miss events that never make into police reports. So this data give us depth, right? So what safe driving actually looks like in the real world. So combining, we get more than 46K balanced training samples, national breadth and real world depth. That dual perspective is what makes this model robust actually. So now let me show you how the score itself work, right? How the scoring works. So we are getting little deeper into the whole, model, right? Let's understand the traditional crash prediction models currently we have, right? So they ask the question, how luckily a crash given the current conditions, and the output is a binary answer like yes or no. But in our safe driver IQ, the green, right? The green right side, we flipped that question into its head. So we ask how far are current conditions from a crash scenario, right? So when you frame this way, the model output, that probability of safe outcome becomes a continuous number, right? Between 0 and 1, correct? Because the safety number is 0 and 1. And then if we multiply it by 100, we get a number, a safety score from 0 to 100. Right? Definitely we have a calibration here, right? And that's what we are going to talk now. So, but just inverting the math is not enough, correct? So we just inverted the math. A pure ML model can actually underweight rare but dangerous conditions. right? So we add a calibration layer on top. These are nothing but like, penalties come from decades of transportation safety research. For an example, if there's an icy road, reduce the safety score by 40%. If it is dark and unlit road, reduce the unlit road, reduce the safety score by 25%. If the driver is driving at a very high speed, reduce the score by 35%. Snow, rain, reduce score by 20%. And if there is a VRU presence, for an example, I mean VRU means vehicle, vulnerable road users. If there are a lot of people around, or cyclists, bicyclists, right? Maybe said during the school times, reduce the score by 12%. So this calibration layer is what makes this score trustworthy in the real world scenario. Right now, let me show you how well the model itself performed. Right, mainly we're moving to the testing part. So see the histogram at the left, we use a sharp value to rank the feature that drives the scoring, right? So the results are really significant. So as you see on this histogram, right, poor lighting is the dominant factor, followed by adverse weather, and then driving at night under dark, and so on, right? Notice one thing, right? What is missing from this list is speed, aggression, and lane changes. So this, three telemetry style feature matters less than driving environment. See, all the top reasons of crashes are environments, poor lighting, adverse weather, night and dark, but none of these are driver behaviors. And we'll come to that part also. On the right, we have the evaluation study confirms this facts, the left side, right? So we retain the model with each feature grouped removed, right? So when we remove lightning, right, the model lose 7.6% of area under the curve, AUC, right? If you remove weather, the AUC removed by 6.5%. Temporal failure, right? If you remove that, it reduced the AUC by 5.5%. But here is a key finding: remove both lightning, the first one, remove lightning, and weather together, right? So the AUC drop 16.4%. Right, so that is larger than combining 7.6 and 6.5. Look at the four rows, right? So remove lightning and remove weather. When you remove both together, it's 16.4 more than if we sum up 7.6 and 6.5. So the learning here is risk doesn't add up literally, it's compounds. So these insights that we have learned through this testing, actually, that road risk is fundamentally non-linear, in environmental factor. So, and one of the most important contribution of this paper, actually, this finding. Okay, so moving to next slide. Okay, this slide brings a framework in life with real scenarios. Let's talk about that. So on the left, we map 0 to 100 score to 50 risk levels: critical, high, medium, low, and excellent. Each level corresponds to a specific actions. A critical score triggers an emergency warning. High triggers as ADAS alerts. Excellent could be qualified for driver for an insurance discount. Say, on the right side, we have 5 real reasons, real scenarios for our test sets scored by the system. Like best case at the top, an average score is 92% when highway driving, when the driver is actually going through an highway. It's noon under clear weather, it's dry, and the speed is low. Average score could be 61% when the driver is driving through an urban road. It is 6 p.m. It is light raining or raining. Road is wet, but no VRU present. As you see, these are the different examples. Worst case is at the bottom. It is 8 when it is an urban driving, early morning, 2 a.m. It is it's snowing, icy roads, VRU presents around, and the driver is driving at a high speed. So it score only 8, safety score. So this is what we learn after observation, that different compounds, conditions are corresponding scores, right? So this is actually a single biggest factor. It observed when there are multiple, reasons get compounded, right? It actually drop the safety score drastically. So this is where the calibration is, penalty for poor lighting or any other, major causes is very important. This is probably the last slide. So the most important, probably the most important one. So findings like 87% of the crashes involve two or more simultaneous risk factor, not only one. Look at the four cars on the top. When a vulnerable road user VRU is present in an urban area at night, the baseline risk get increased by 4.5 times. If it is night and adverse weather, baseline risk increased by 3.8 times. If it is urban driving during rush hours, baseline risk increased by 2.5 times. Right. So the bottom line is that the risk multiplies. And the second finding is even more surprising. So we clustered, to 213K crashes record by driver behaviors, and we found three different driver behaviors. The first cluster is cautious but crashed. So 30%, around 30% of the crashes involve drivers are due to road or bad weathers. So in these cases, driver actually, shows near zero aggressions within speed limit, driving with the speed limit. So there are no other reasons from the driver's side that can cause the crashes, but only the weathers and environment. Second is the environmental risk takers. Like 47% are this type. So these are the drivers who choose to drive in a bad weather conditions, and even though they can avoid that, right? So it is the choice, not the bad driving. And finally, around 23% fits the stereotype of aggressive driver. So this finding is significant. Most crashes are not solved by punishing reckless driving, right? So that's the conclusion. Because most crashes involved driver were not reckless, they were solved by giving every driver the information that need to make better decisions in real time. And that is where safe driver IQ comes into picture. Yes, that's the last slide. Conclusion. So as we discussed, environment beats the behavior. Environment is the main cause of a lot of most of the accidents, more than close to around 70%. So inverse modeling works. So a binary crash classifier involved in 0 to 100 score is viable. We tested, it is successful. A reusable paradigm, right? So inverse modeling is not specific to driving only. It's a binary risk classifier. It can be, used any domain like medicine, finance, and cybersecurity. And future work, we expand the Waymo data, right? We used less data, right? 500 real use test scenarios. We need to expand it. Fuse live telemetry and GPS, field validation with fleet operations that needs to be done also. And replacing the heuristic calibration score, right, with data-driven PAT scaling. And the fifth one, which is not visible here, that we need to expand this research not only for the US road, but road across worldwide so that it can cover multiple scenarios. With this, I'll rest this topic. Thank you, everyone. You have actually a barcode here, QR code here, if you want to connect me through LinkedIn. Rather, also I can open here to address any questions that you have. I will stop sharing. Thank you,
Thank
everyone.
you, Johit. Johit, maybe, well, I'm working in this area, so I'm really attracted and interested in your research. However, for the sake of time, maybe we can switch to the next talk and then have questions at the end, if everyone is fine. Okay. Okay, great. So thank you again, Jajit, and let's leave the floor for the moment to Dixon or Suchang for introducing the next speaker.
Yeah, it's my pleasure to introduce today's speaker, Professor Wenxin Guo, from UNG University, Taiwan. And Professor Guo is a professor in Department of Electronical Engineering at UNG University, and he is also IEEE senior member. He received his PhD in electrical engineering from National Taiwan University. He research focused on the next generation wireless network and 5G, 6G access technology and resource allocation and IoT, vehicular network, and end-to-end communication. Today, he will present on the next generation VR streaming optimization via multi-base station coordination. Please let me in giving a warm welcome to Professor Guo.
Hello, thank you, Professor Pai, and thank you, everyone. And it's my greatest honor to have a webinar talk here. So can everyone see the screen and hear my voice? Okay,
Yeah, I can
then
hear you.
Yes.
Cool. And then I will start my presentation. So thank you for joining this CTSoc webinar. And I'm Wenxin Guo, and I'm from Yuanzhi University, Taiwan. And it is my greatest honor to give a talk here. So here I would like to show the recent search on the VR, MR streaming optimization via multi-base station coordination. So let me start with the motivations. So immersive VR and MR currently demand exponential bandwidth. So I want you to imagine that there are many users wearing the VR or MR goggles, walking around in a theme park or something. And if this kind of things want to become reality, then the traditional single base station, like the left side, is not that feasible because it will simply collapse under the load of dense user clusters. So if you want to deploy multiple base stations around these user devices, then you still face some new challenges. These new challenges include spectral bottlenecks, uncoordinated redundancy, and some waste of the system capacity and low imbalance and different issues over there. Okay, so that's why we separate this into three different challenges. So in the first challenges, we assume that everyone was watching the same panorama videos. And in this case, we can do something, for example, to multicast to save the frequencies, save the bandwidth. And in our second challenge, in our second work, we think about assuming that everyone was watching different contents. So in this case, we use a different approach, which means that we use the scalable video coding, which means layer encodings to reduce the resource consumptions. And in our third work, we even use the volumetric video types, volumetric videos, so that we separate the watching area and predict the watching direction of users viewing contents, so that we can save the resource in a more efficient way. So we separate the challenges into three different. We separate it into three different challenges. Okay, so let's go to the first one. Okay, so in our first topic, we assume that everyone was watching the same panorama videos, but in different directions. Because as you know, in this panoramic VR movies, everyone is free to look around in different directions. So instead of multicast, but since they are the same, watching the same contents, we can do the multicast. But instead of multicasting all different angles, for example, the all 16 or 32 angles, we transmit only few selected anchor views and use a technology called depth image based rendering, DIBR, which means that we can synthesize the viewing angles based on the adjacent angles on the the VR goggles. So in this case, we shift the computing overhead to user's device to save the transmission resources. And in this case, the computation overhead remains easily feasible for mobile device, and base station only multicast some given views. And the chip inside the headset uses this DIBR to dynamically synthesize the exact desired viewing viewing angle of the local users and saving resources. Okay, so given these technologies, we develop these algorithms. So this algorithm has two phases. The first phase is it literally extract the allocation with the maximum marginal utility per antenna and finds the best allocation strategy of each viewing angles. And then given different base stations, we can allocate which direction to different base station and use them to multicast to the user in this service area. And combining together, we can have a very efficient allocation strategy so that everyone, by receiving the multicast viewing angles and synthesized by themselves, and everyone can watch in different viewing directions. So moving forward, we combine our algorithms with AIs. So we use an AI DDPG agent to switch our proposed algorithm with other algorithms under different cases. So for some, when low latency is needed, we use a best channel first policy. And in some case, we use our policies. And in this case, we can even have more performance gains. So comparing with the baseline, as we show in the left bar, our UMVS algorithm has more 10% gain, and combining the AI, it has even more 6% total performance gain. Okay, so this is our first challenge. So in our second challenge, everyone was looking, watching different contents. So in this case, multicast is not feasible because everyone was receiving different content. So in this case, if you want to save the resource, radio resource, we have to make the resource, we have to improve or increase the granularity of the radio in source. So that's why we use the scalable video coding and divide the video streams into multiple layers. Okay, so this is called scalable video codings, and we let different base station to assign different layers. Okay, but the problem is that how do we assign the layers? We have a policy-based mechanism. So starting with the network, which has starting with the base station with the least subscribers, which means that it has the lowest allocation flexibility. So we start with this kind of BS and let them to optically allocate the resource, and then for other BS. And in this kind, by doing this iteratively, and until the all resource is exhausted, then we can finish the resource allocations. So so in one word, we let it serve the most unsatisfied user first, and then solve the allocation problem and iteratively. Okay, so here's the result of the our second proposed scheme. So as you can see here, the DMUN, which is our proposed scheme, it has the highest total utilities comparing to different baselines. And also, when we change we let the bandwidth of the subscribed videos keep fluctuating like this gray line. And when as this up and downs, all baselines, they have very unstable fluctuation. And our proposed scheme not only has the best utility, but also have the best stabilities. Okay, so we not only show it in the simulation, we also prove it by providing some analysis showing that our proposed scheme has a very good stabilities, so that the bandwidth of one single VR users will not affect other users. Okay, so this is our second challenges. Okay, so let's go to our third challenge. So with the third one, this one, we not only separate each videos into different layers, but also given that everyone keep moving and watching, and so that's called a 6 degree of freedom viewing port. So to optimize the views, the tile views and the layers, we have to anticipate the viewing direction so that we can only transmit the range that the user will be viewing in the very nearest future. So in this case, this is the most challenging one. We have to predict the viewing angles of the users. And then basing on the predictions, we can do the resource allocations. Okay, so this is our third work. So the first part is to predict the field of view, the range of the videos the user will be viewing. So we construct a neural network and use a set of the GRU, a gated recorded unit neural network, to forecast users' 6th viewport. So starting with users' past movement, which is on the left side, and then we use a set of the GRU networks, and they will not only predict the viewing coordinates of users' next steps viewing angles, but also the prediction confidence, which is very important because we use this to calculate the expected value of the utility of each tiles. And basing on the expected value of the utility, we conduct the resource allocation. That's the main idea. Okay, so this is the prediction part. And basing on the prediction part, we do the resource allocation. So the resource allocation is to, we let each base station the idea of the resource allocation is we let each base station to start with the viewing tiles with the highest utility, and then we started and do the resource allocation. But the problem is that each different base station may have may do the overlap resource allocation, which means one tile may be allocated by multiple base station, and so we have to release this part of the resource and then include more tiles or layers, and this will be repeated until all tiles are not overlapped and all available resources is allocated. And in this case, we also conduct the analysis to show that our proposed scheme has a limited gap to the theoretical optimal solution. Okay. So basing on this, our numerical results show that comparing to standard baseline unicast approaches, our volumetric tiling and field of view prediction can provide more than 50 or even close to 60% of performance gain. And this based on the very accurate AI prediction of the viewing angles. And we should use the actual VR 3D movies or VR games to show that we can actually predict very accurately of the next viewing angles, next moment's viewing angles of each users. So basing on these predictions, we can provide very good performance gain, which means that you can only by transmitting only the range that the user will be viewing, then the quality of experience of each user can be greatly improved. And also by the multi-base coordination, which means that we release the overlap resource and to include more layers or more resources, then it can provide more 15 to 20% performance gains. And so that's why our proposed scheme can provide up to maybe 70% performance gain over standard multicast baseline. Okay. So this is the spotlight of the good part of our third research. Okay, so to summarize, the bandwidth demands of the next generation VR and AMR means that the single base station network is obsolete. So we must bridge the gap between the video layers and the physical network layers. So by combining the DIBR, which means the view synthesis of the multicast 3 panoramic videos, and also using the layer encoding for the unicast streaming, and also combining the tiling and the view angle predictions, we can achieve massive and stable real-time efficiency gains. Okay, so this is the main idea of today's talk. And finally is it's our reference, and I invite all of you to read our full papers for this for some mathematical proofs and theoretical analysis and detailed system architectures. And the first one is about the multicast DIBR synthesis, and the second paper is about the layer encoding one. And the first one is published on the transaction on mobile computing, and the second one is published on the transaction on the next network service management. And the third one about the view angle prediction is just we just get accepted in the last months, and it will also be published on the transaction on network service management special issues. And for now, thank you for your time, and I'll be more than happy to open any questions you might have. Thank you very much. Thank you very much.
Thank you. Also to you, Win Think. By the way, I started my research on remote rendering, and I'm working on VR. So this topic are, maybe 25 years ago, we were working, before this technology actually ramped up, that we were working on enabling VR on PDAs and limited resource devices. So that's really that's very interesting, and it's very nice to hear that research is still so active in this area. So thanks to both of you. I think we have not so much time for questions. Maybe one for both our speakers. Is there anyone who wants to go first? If not, I can start with a question for our first speaker. Well, I did some work in this area, working with some insurance company, Jajit. And so I'm wondering, well, I have many questions. I would have many questions for you, but which are, based on your experience, the most predictive signals for, driver scoring? So which are the most insightful features that characterize this risk level for drivers? You are mute, so yeah, it happens. We cannot hear you yet.
Oh, I have to unmute myself. Sorry.
Great.
Okay. Yeah. So see, the biggest risk factor is always snow and icy roads, but that is very rare to happen. The most common factors, as per these findings, is dark and unlit. Basically, it's no light and dark, and mainly happens when things are getting darker from
So these
daylight
are
to dusk.
about environmental conditions and
It is
regarding.
environmental. Is the poor light is the main reason, and not poor light that you started at the night, right? It's mostly happen when you are driving, and throughout the driving time, the sun goes down and it's getting darker,
Mhm.
right? That's the time is most of the accident happens. That's the findings, right? And I think it is finding by many research also, not only this, but the whole point here is that we need to give a scoring system. It's you cannot explain a lot of things on the screen when driver is driving, right?
Mhm.
But you need to give some kind of score, right? That can alert the driver, oh, my score is very low, less than 70, 60, 50. So I need to, and then, right, driver will be attentive, and he probably can himself understand that what kind of mistakes he's doing. And based on that, he can try to rectify. Sometimes you can go ahead. Implementation part is not yet not discussed, right? You have the reasons that why the score you are giving, right? Maybe if once you get the driver attention, you can flash the reason in 1, 2, 3 words,
Mhm.
something like that, right? I see road, right? Getting darker, right? You are speeding, something like that. Stop speed, whatever. That is
Yeah.
yet not implemented, but we are having actually another paper, planning for another paper to submit, right? And there is automobile center of you know excellence is also involved from US on
Mhm.
this. One of the VP of the R&D department, right? He is also a part of this research. So yeah, we have been actively trying to work on do something meaningful where it can reduce the number of accidents.
Sure. Okay. Thank you. Very interesting. Um, do you have questions for Professor Kuo? Well, actually, again, I have many, but you talked about prediction of the point of view.
Uh,
Are we able to work? Are you able to work also on the gaze? So, are you able to do something on? Maybe you mentioned it, but I missed. So, is there a possibility as well?
you mean
The where the user is actually, so the viewpoint is typically, it applies to any kind of can apply to many types of experiences, but also being able to determine where the user is actually gazing at, it's much more or maybe it's included in what you're doing already.
No, we actually doing with the field of view, so which means the range. The
Mhm.
range,
Okay.
yeah. If you want to do the gaze, you said the first one is that you have to use the special devices that can detect the eyeballs, right?
Exactly.
Yeah, but in theory, I believe it is not that difficult because it is the trail of the eyeballs is continuous.
Hmm.
Yeah, so I think maybe if the gadget is available, then maybe it is possible to it may be even easier than the field of view. Yeah, but the problem is that on the aspect of the transmission, we are not sure if this is that important because for the field of view is the part that you want to transmit. Yeah, but maybe you're right because for the eyeballs we can provide the more high resolution data on that area, but still it had
Exactly.
but because there are some latencies, so we have to do more experience and research on it. But thank you very much. It will be a very
Yeah,
good
the
direction.
problem is that you might have, then there are also headsets that have higher resolutions
Yes,
in
yes,
some portions of the screen, but
yes.
indeed you have very frequent, very high frequency movement, so you might not be able to do something helpful because when you try to compress more in one part, then the user is looking or compress less in one part, the user is looking already somewhere else. So, but that could be something interesting to
Yeah,
explore.
exactly. I think that there will be maybe there will be
Mhm.
something we can look into it in the future. Thank you very much for your
Okay.
suggestion.
So I think we are exhausted our time. So let me thank again our speakers, Mr. Roy and Mr. Kuo, our VP, Mr. Dixon, Professor Dixon Lee, Professor Park as Vice Chair of the CCN TC, and all those who attended today's call. It's been a pleasure. Next webinar will be in about 1 month. You will receive information, and this material will be published online, so everybody will be able to, enjoy it. Thank you once
Thank
again.
you.
Bye
Thank you.
bye.
Thank you very much.
Thank you,
Thank
Thank
you.
everyone.
you.
Bye
Thank you.
bye.
Thank
Thank
you. Bye bye.
you.